So now let's work through a problem where we're given the position of an oscillating mass as a function of time, and then we want to solve for the amplitude, period, and frequency. In this problem, the position as a function of time is 2 times the cosine of 4t. So that means that the amplitude is 2, so the maximum value of cosine is 1, so the maximum value of the function here is 2 times 1. And so we're basically just plugging into this formula that we used before. X is equal to a cosine omega t, so that means that whatever is in front of the cosine is our amplitude, and then whatever is inside of our amplitude times time is going to be the angular frequency. So, alright, so that means, secondly, that omega here, is 4. So the angular frequency is 4 radians per second. So if we're trying to do an estimate, just to give us a sanity check on what is going on, there's about 6.28 radians in a circle, so the period of the oscillation will be about 1.5 seconds, right? It takes 4 radians per second, so to reach 6 it's going to take about 1.5 seconds. So yes, this is just to keep an eye on our numbers and make sure it comes out reasonably. Now we want to find the frequency. So the frequency is the angular frequency divided by 2 pi, so it is 4 over 2 pi, so the frequency is about 0.64 oscillations per second. If we know the frequency, we know the period. The frequency is the number of oscillations per time, and the period is the time per oscillation, so they are inverses of each other. So the period is 1 over the frequency, so 1 divided by pi over 2, so that gives us a period of 1.57 seconds, or pi over 2. I think the main point here is to try and understand the relationship between the angular frequency, the frequency, and the period. The angular frequency, or angular velocity, is the number of radians per second for the oscillation. So once that has reached 2 pi, then the cycle repeats itself. That means that if you divide 2 pi by the radians per second, that means you're given the period in seconds. If we want the frequency, then we can take the inverse of the period. The period is the time per cycle, so the frequency is the cycles per second. Also, we can go directly to the frequency by dividing the angular frequency by 2 pi to get the frequency. The next problem we want to do is when a 200 gram mass is hung from a vertical spring and then pulled down 10 centimeters from the equilibrium and released. The period of oscillation is 0.5 pi seconds, or about 1.6 seconds. Find the spring constant k. So the angular frequency is the square root of k over mass, so we need the angular frequency. The period is 2 pi over the angular frequency, so that means that the angular frequency is 2 pi over the period. So 2 pi over 0.5 pi gives us a angular frequency of 4 radians per second. So we know the angular frequency and we know the mass. That means we can then rearrange the formula for the force constant is equal to the square root of k over m, and we solve for k and we get that k is equal to m omega squared. We will then want to convert k to kilograms, so that's going to be 200 grams is 0.2 kilograms, and this becomes 0.2 kilograms times 4 radians per second squared, and if we do that, we get 3.2 newtons per meter. Notice we need kilograms to find the force here in newtons. So yes, that's how we solve these. I think the big challenge is recognizing the difference between the angular frequency, and the period, but once you get that down, these questions aren't too bad. Alright, so you have some questions to do, and next we're going to take a look at the energy.